Chapter 8, Image Post-Processing and Visualization Tools. Image post-processing refers to various techniques that modify reconstructed images displayed for viewing and interpretation. This does not produce more information content. The original image always has more information content than the processed image. It uses axial data sets stored in the computer to produce the 2D and the 3D images. Image processing operations such as point, local, and global are either linear, and they also can be nonlinear. The linear includes image smoothing and image enhancement, and the nonlinear deals with grayscale manipulation, where the grayscale of the image can be modified with different algorithms. A common algorithm used in CT by techs and by RADs is based on a point processing technique, and this is called grayscale mapping. This is also known as windowing. The CT image is reconstructed from the projection data collected from the patient, and the result of the image reconstruction is a numerical image. This numerical image must be changed into a grayscale image in order to be viewed by technologists or radiologists. The numerical image consists of a range of CT numbers, which are also called gray levels, and these numbers are converted into grayscale, with the lower numbers assigned to black and the higher numbers assigned to white. The picture contrast and brightness are easily changed with the two control mechanisms that are called window width, which controls the contrast, and window level, which controls the brightness. Window width is the range of CT numbers on an image. It determines the maximum number of shades of gray that can be displayed. A large window width means that there is a long grayscale, so the transition between the lower CT numbers, which are black, and the higher CT numbers, which are white, is large. A high window width, I'll just draw this arrow in right here. A high window width equals low contrast. So basically, as the window width increases, then the contrast decreases. So there are lots of shades of gray. Low window width, on the opposite side of things, means that there is higher contrast. So when the window width is decreased, then the contrast decreases. So this means there are fewer shades of gray, ultimately meaning there's more black and white. A narrow window width means the transition from black to white will take place over a few CT numbers. And I want you to take a look at figure 8.3 on page 160 of your book to see what I mean. Upper and lower limits of gray levels can be calculated, and they each have their own formula. The upper gray level values are calculated with this formula right here by taking the window level plus the window width and dividing it by 2. And the lower gray level values are found by window level minus window width divided by 2. So in the image shown here, image A, you can see has higher contrast, which means it has a narrow window. And I know this because it has fewer shades of gray. And the image on the right, image B, has low contrast because it has a wide window, meaning that there are more shades of gray. So this one has more black and white, which means less shades of gray. This one has more shades of gray. Window level is the center or midpoint of range of CT numbers, also known as the reference point. When window level is centered on lungs, the image displayed is optimized for that structure. So when it is centered on the pelvis, for example, then the image displayed is optimized for the pelvis, which the pelvis appears white and the lungs then appear black. As the window level moves towards the higher CT numbers, so the white numbers, then the more CT numbers with lower values are displayed. So these lower values are generally black. As the window level moves toward the lower numbers, more CT numbers with higher values are displayed and the image looks white. In the picture shown, image A, right here, shows when a narrow window width is useful, like when possibly looking for pathology in the lung. And you can see the vessels actually are seen much better in image A here than image B, and the narrow window width allows this. CT number range varies among scanners. For bone structures, the window width must include the higher CT numbers on the scale, and for structures that include air, the window width moves toward the lower CT numbers on the scale. The window level can fall anywhere on the scale, depending on the structures of interest. Wide windows should be used to show tissues of greatly differing attenuation within the image. Example, body scans, lung and bone, in order to include air spaces and vessels for the lungs and the cortex and marrow for the bone. Narrow windows should be used to display soft tissues with structures that contain different tissues of similar densities. An example is the brain, to show differences between gray and white matter. Levels should be centered near the average attenuation of interest. Take a look at figure 8-9 in your book. Preset windows are available on scanners to optimize windowing. An example is a dual window display, which shows two different density ranges at the same time for two different anatomical areas. And both windows have different window widths and window levels. It separates two anatomic areas well, so the observer can view bone and soft tissue windows of the same images at the same time. Multiplanar reconstruction is a computer program that can create sagittal images, coronal images, or periaxial images from a stack of contiguous transverse axial scans. The sagittal image divides the body into right and left sections. The coronal image divides the region into anterior and posterior sections. The periaxial image is a plane that passes through the coronal and the sagittal planes in a longitudinal direction. Irregular views, oblique views, and other views can also be generated. The irregular view can be reconstructed from a stack of contiguous transverse images. Take a look at figure 8-18 in your book for an example of this. And the oblique view, or also known as the oblique view, depending on what you prefer, can be reconstructed with at least 3 arbitrarily defined points in different transverse images. And figure 8-19 lays this out well. And just taking a look right here, image A shows a coronal image, and image B shows a sagittal image. There are pros and cons to reformatted images. An advantage to reformatted images are that they enable the visualization of specific structures such as optic nerves in relation to the surrounding structures. Another advantage is that the reformatted images determine the true extent of lesions or fractures to help localize lesions and intra-articular bone fragments of foreign bodies. One disadvantage is image quality. Image detail is not as good as that obtained in transverse images. The reformatted image quality depends on the quality of the axial images, which is why it is even more important that the patient stays still and holds their breath when they are supposed to during the exam. Also, plane thickness affects the image detail. Thick planes result in blurring and loss of structural detail. However, multi-slice scanners that are capable of isotropic imaging solve these issues. Now on to 3D imaging, which we will only get into briefly since we will discuss it more in a later module. 3D imaging is used when the desired image is either physically impossible or impractical to acquire. To display the 3D images on a 2D television screen, special software gathers information from the transaxial scan data. 3D imaging is used in CT, MRI, and other modalities to provide both qualitative and quantitative information from images to facilitate and enhance diagnosis. The general framework for 3D imaging requires 4 major steps. The first one being data acquisition. Second one being the creation of 3D space. Third, processing for 3D image display. And fourth, 3D image display. Images can be displayed as projection images, such as maximum intensity projections, or MIPs, minimum intensity projections, or MINIPs, shaded surface display images, SSDs, and virtual reality images. Basic visualization tools are basic computer programs integrated into the computer system with the following capabilities: multiple imaging and multiple windows, image magnification, evaluation of geometric characteristics such as distances and angles, superimposition of coordinates on the image to provide biopsy references, and highlighting, which is where pixels in certain regions of the image can be made brighter. Some of the basic visualization tools include the CT histogram, which is a plot of pixel values, and this can be done for the entire image or just the region of interest. The region of interest statistics, which allow for statistical calculations within the ROI, for example, the mean or the standard deviation. The ROI transfer, where the ROI can be transferred from one slice to another slice. There's split imaging, where the image can be split into two detailed thin slices. And fuse imaging, where two continuous thin slices can be fused into a single thick slice. Advanced visualization tools require powerful workstations with advanced image processing capabilities and increased memory. 3D rendering is an example of one of these tools, and there are three categories: shaded surface display, virtual reality, and the MIPS and MINIPS. Computed tomography and geography is another tool. This is known as CTA, and it is based on volume scanning principles. To go into the CTA tool a little further, there's 4D angio, which is a fourth dimension, and that is opacity. Then there's vessel tracking, which allows users to produce a set of NPR batches for the entire vessel. There's skull removal, which subtracts the bones of the skull from the CTA image to allow visualization of every detail of a vessel and soft tissue. Then another visualization tool is Cine, and the Cine visualization tool allows users to view large sets of images very quickly. Interactive visualization tools offer the following features in any 3D rendering mode: window level adjustment, volume of interest adjustment, scan information display, movie creation and playback, split screen presentation, zoom, and measurements. Advanced quantitative measurement tools, they allow measurements such as distance, angles, areas, standard deviation, and minimum and maximum voxel values. Multimodality image fusion tools is another advanced visualization tool, and this combines images from various modalities such as CT, MRI, PET, and single photon emission CT to facilitate diagnosis of tumor localization and quantification, surgical planning, and oncology planning. Then there is the virtual reality visualization tool, which creates 3D and 4D images of tubular structures. An example of this is CT virtual endoscopy, and it allows users to actually fly through images of hollow organs. It's pretty neat.